In this video, we're going to introduce the representation of signed integers as bit strings, and we'll also discuss addition within this number system. Recall that machine integers are represented as fixed-length bit strings. For example, in C, signed ints are represented as bit strings of length 32, which means that there are 2 to the 32 distinct signed ints. But for simplicity, let's suppose we're working on a hypothetical machine with 4-bit integers. Using 4 bits, we have only 2 to the 4, or 16 different bit strings. It's convenient to represent these on a number wheel, as shown here. We'd like to use our 16-bit strings to represent some positive and some negative numbers, around the same quantity of each. So we need to figure out how to do that. The 2's complement number system is a convenient approach. In 2's complement, we treat the bit string as a binary number using positional notation, but with the following quirk. The high-order bit has negative weight. For example, consider the representation 1010. This stands for -1 times 2 cubed, plus 0 times 2 squared, plus 1 times 2 to the 1, plus 0 times 2 to the 0. That equals -8 plus 2, or -6. Notice that whenever the leftmost or high-order bit is 0, this gives the same value as for an unsigned integer. But when the high-order bit is 1, that indicates that we have a negative number. Using this convention and our 4-bit system, the 16-bit strings represent the 16 integers from -8 to 7. Notice also that there's one more negative integer than positive. We can use this representation to do machine arithmetic. Suppose we want to add 2 numbers, say 2 and 3. Starting at location 0, we move clockwise 2 positions. To add 3 to that, we simply proceed clockwise another 3 positions, and we end up at 0, 1, 0, 1, which is the representation of 5, the expected answer. Let's try another one. Suppose we want to add 4 and 5. We move clockwise from 0 to 4, and then clockwise another 5 steps. This lands us at 1001. But in our 2's complement representation, this is -7, which clearly isn't the right mathematical answer. So what went wrong? Well, nothing. That's simply how this system works. In this system, the mathematical answer, 9, isn't represented by one of our bit strings. Instead, we had an overflow from the positive into the negative range. Now suppose that, instead of using the number wheel, we had just added the 2 representations using binary addition. We see that 4 is represented by 0, 1, 0, 0, and 5 by 0, 1, 0, 1. Let's add them using standard binary addition, starting at the rightmost position. 0 plus 1 equals 1, 0 plus 0 equals 0, 1 plus 1 equals 2, but in the binary number system, that's 1, 0. So we record 0 and carry the 1. Finally, 1 plus 0 equals 1. Again, we're left with 1, 0, 0, 1, representing -7. Let's try another one. Suppose you want to add -4 and -5. Adding a negative number means moving in a counterclockwise direction around the number wheel. Start at 0 and move counterclockwise 4 units to -4. Then move 5 units counterclockwise to 0, 1, 1, 1, or 7. Here we got an overflow from the negative range into the positive range. But is that the right answer? Well, in this system it is. Let's check it by adding our representations. On our number wheel, we see that the representation for -4 is 1, 1, 0, 0, and the representation for -5 is 1, 0, 1, 1. Let's add them. Notice that we get a 5-bit sum, but we can only store 4 bits, so we truncate by dropping the most significant bit. That gives us 0, 1, 1, 1, or 7. The processor may also record that we got an incorrect mathematical answer, a negative overflow in this case, by setting the overflow bit. The lesson here is this. In the 2's complement system, we can add numbers by simply performing binary addition on the representations without worrying about positive or negative. By the way, at the level of bit strings, we do exactly the same operation for unsigned. That means that we can use the same hardware and even the same operation to do addition for signed and unsigned integers. Of course, what we've said about our 4-bit integers applies as well to 32-bit or 64-bit integers.